kids, welcome to day 2 of our Cauchy-Euler equations. Do you see the difference? Yeah, non-homogeneous. So what did we do when we had non-homogeneous before? What did we do? Our go-tos were the method of undetermined coefficients and the method of variation of parameters, right? Method of undetermined coefficients were when we had a linear combination of polynomials or E stuff or sine and cosine, right? Method of variation parameters, we could do method of parameters with any of those, but also for other kind of weird functions. But sometimes that would mean that we would have to leave our answer in terms of an integral. So not ideal. So we always would try the method of undetermined coefficients, hope for that first, right? The problem is that it starts off the same, right? Where if we have this, we kind of look quadratic-y here as coefficients. When we were doing undetermined coefficients and the methods on an MVP, we had constants in front of here. If you don't have constants and you're trying to relate things where you've got to, right, multiply by functions in terms of x, ew. So what we're going to do is a transformation that is going to turn these functions into constants. So let me show you how that looks like, right? Somebody came up with this. His name was Cauchy. Let's do a transformation where we assign every x to be e to the t. And then, of course, solving this equation for t gives me ln x. And we're going to assume that x is greater than 0. Notice this has it, right? Our Cauchy-Euler have a point of singularity at 0, so we're not going to be choosing x to be 0. But anywhere else, we are going to use this. And so we're not going to use 0. If we wanted to use negative x's, we would just use the let x equal negative e to the t, whatever. We're just going to stay positive here, okay? So I want you to look at this math I've done. I'm doing a differential equation. So I'm given y, and my goal is to try to come up with y equals, right? My solution is y equals. So all these derivatives, right, are in terms of x. The derivative of y with respect to x. But remember from BC, right, BC Calc, that the chain rule says the derivative of y with respect to t times the derivative of t with respect to x is the same thing as dy dx. Do you see that? But look up here in purple. I can find the derivative of t with respect to x, can't I? Do you see that? Here's t. What is the derivative of t with respect to x? Well, that's 1 over x. So I just took this equation and I replaced dt over dx with 1 over x. So y prime. I need y double prime though. So the second derivative of a product is the product rule. So it's dy dt times negative 1 over x squared, because that's the derivative of 1 over x, plus 1 over x times the derivative of this y with respect to t, which means there's already one derivative. You need to take its second derivative. But remember, I'm after the second derivative of y with respect to x, so I'm going to do the same thing with my chain rule. The second derivative of this y with respect to t times dt dx is going to be the second derivative of y with respect to x, and I'm just going to float this squared over here when I'm done. But our dt's are going to cancel out again, right? And then this is going to end up being a squared. And that squared isn't really squared as you think of it. It's indicating the second derivative. So I'm going to, again, fill in 1 over x. And then I'm going to factor. Do you see that I have a 1 over x here? I'm sorry, a 1 over x squared. But on the other side of the plus sign, I always also have a 1 over x. Sweet, right? So I'm going to factor out this 1 over x squared. Let me get this out of the way. So here's the 1 over x squared I factored out front. Then I have the second derivative with respect to t minus the first derivative with respect to t, right? That's all in here. Now I want you to look at some things, right? Oops, that's not what I wanted to do. Look at these two boxes. I have this y prime is dy dx, but I got it equal to a derivative of y with respect to t and multiplied times an x thing, right? I kind of sort of sucked out the x part. And do you see that I did the same thing here? So I'm going to put these two boxes on top of my next slide, not changing it. But remember, I want to transform everybody into t, right? To deal with these t's, specifically e to the t, right? Because of derivatives, I'm so nice with those. Well, I have an equal sign. I want you to multiply both sides of this equation by x and both sides of this equation by x squared. And look at what I get. Oh, snap. Look at my original equation that had x's in it and derivatives in terms of x. X squared y prime I can replace with just derivatives of y with respect to t. Oh my goodness. Xy prime I can replace just with a derivative of y with respect to t. Y is what I'm trying to get by itself, so that's fine. And then this g of x does have to be, I have to replace that x with e of t. What? So let's go ahead and substitute. A times x squared y double prime, which had x's and derivatives in terms of x, and I replaced it with derivatives and just in terms of t. B times xy prime, that's what that is. Cy is equal g to the compose in e to the t to that right side. Distribute. Should start to look familiar. A factor. Oh, snap! That looks really familiar to what we've just been doing. I just copied it over. And I don't want to get these A, B, and C's mixed up here, right? I mean, this A, B minus A, and C does come from up here, but I'm going to be dealing with a differential equation where I want everybody in terms of t. So I'm going to write it that way. But notice what the deal is going to be. Can you tell already? A, B, and C are going to be constants. I'm going to be able to use the method of undetermined coefficients just like I did in chapter 3, because it's only second order, certainly not chapter 4 stuff. What? Let's do an example. All right, up here in X land, little a is 1, little b is -2, little c is +2, and x squared is g of x. Let's do our transformations. Capital A is the same as little a. Capital B is little b minus, oh, I didn't want to be that color. Little b minus little a. C is still C. But g of e to the t, right, is e to the 3t. So let's write our new purple equation. Oh, I should have been writing all that in purple. One y double prime minus 3y prime plus 2 is equal to e to the 3t. Our characteristic equation is r squared minus 3r plus 2 is equal to 0. That's going to get our homogeneous solution. Now we're going to use our method of undetermined coefficients to get our particular equation. Our particular equation is of the form e to the 3t. Find its derivative. Second derivative. Substitute in to purple. You're in purple t land. 9a e to the 3t minus 3. Whoops, it's supposed to be a y, isn't it? So what do I have? 9 minus 9 plus 2a e to the 3t is equal to 1 e to the 3t. So a must be equal to 1/2. So my particular solution which means my actual solution, my complete solution, looks like that, right? Careful. You started in X land, so you need to go back and transform the X's, right? Your actual solution, what's e to the 2t? That's e to the t squared, right? E to the 3t is e to the t cubed. There's your actual solution. Crazy. Let's do another one. If you want to pause the video and see if you can do this yourself, right? We're going to do our transformation where little a is 1. I'm sorry, capital A is the same as little a, which is 1. Capital B is little b minus a. Capital C is the same as little c. For ln of what? Which is just 4t. Right? So our transformed equation is 1y double prime plus 3y prime plus 2y is equal to 4t. Characteristic. Particular, right? Polynomial. So at to the first plus b. Gotta love this when this happens. Plug back in to purple. So what do we have here? 2a must be equal, whoops, 2a, because that's with the t, must be equal to 4. So a is 2. Remember, this is plus 0, so what do I have? 3a plus 2b is equal to 0, but a was equal to 2, so that's 6 plus 2b is equal to 0, so b must be equal to negative 6 divided by 2, negative 3. So y is equal to, nope, don't forget to check this box, or I guess check that thought bubble. My actual solution is y is equal to c1 x to the negative 2 plus 2 what? And then minus 3 is just minus 3, yeah. No transformation necessary there. Woot! All right, let's do one more. Because this time, what happened? Initial condition, right? So again, if you want to start the video and then come back, pause the video and then come back and see if you get what we get. Capital A is little a, capital B is little b minus little a. Capital C is little c. So I've got y double prime with characteristic. Particular. Don't forget to check, make sure you don't have any overlaps. Whew. Always hated when that happened. Substitute in up here to your purple equation. Nine minus 18 is negative 9. Negative 9 plus 8 is negative. A is going to be equal to 2, so A is equal to negative 2. So my purple solution looks like that, but my actual solution looks like that. And I'm done except for these points, which by the way are in, right, X land. 2, 0, 2, negative 8. So I'm going to erase my work here. Right, again, y was equal to c1 x to the 4th c2 x squared minus 2x cubed, plug in 0 and 2. So when I was done with that, what is this? 16, 4, 8, 6. So I'm going to end up with 16 is equal to, right, because that was negative, I'm going to move that over, is equal to 16C1 plus 4C2. The first derivative -8 and 2. Oops, I forgot. Squared. Cubed. So what is that? That is 32 C1. Oh, this is nice. 4C2, and then what is this? 4 negative 24. Add that, so that's also going to be 16. Well, this is nice. I can just subtract down, and who cares what C1? That's going to go away. So whatever. Negative 16 C1. C1 is equal to 0. Plug back in. C1 equals 0 up here. So I get 16 is equal to 16 times 0 plus 4C2. C2 must be 4. So now I'm going to take these up here, which is going to eliminate the x to the 4th. Gee, I feel like I worked so hard to get that. And C2 is going to be 4. Gee, a lot of work for that. All right. So a couple examples of just doing, Cauchy-Euler and using a transformation to get ourselves into constant coefficients so that we can use our method of undetermined coefficients. I didn't do any of these with MVP, right? Because they were all E things. So I could have, but I would have just made more work for myself. I won't do MVP unless somebody makes me. Or unless I have to, because I don't have any E's, sines, cosines, or polynomials, right? All right, I will see you in our live session.